Everybody's turned in? Get my... All right, so how about that first one? We're going to do U substitution on both of these, right? And on the first one, what is the U that you're going to use? X cubed plus 1? So if you make ux cubed plus 1, the derivative of that with respect to x is 3x squared. So you could rewrite this as du equals 3x squared dx. Right? And you have x squared dx here. You're trying to see if you've got that over here. If I rearrange this, then you have it right there. So we just need to get rid of that 3, so we scale both sides by a third. And then I rewrite the entire problem. So the problem becomes integral cosine of what? U times this, which is 1/3 du. And what can I do with the 1/3? Take it out. So 1/3 integral cosine u du, antiderivative of cosine of u. So just sine u plus a constant. And then replace u with 1/3, x cubed plus 1. So there we go. Do what? Are you talking to yourself?
We're just discussing.
Forgot plus c? Okay. Questions?
Yeah, I think we forgot this.
So there are some professors out there that will count it completely wrong if you forget c. I won't count it completely wrong, but I won't give you full credit if you forget c. All right, so that's that one. Any questions on this? All right, the next one was sine x over 1 plus cosine squared x, right? So use cosine x. The derivative of that is negative sine x. Right? And then I have that over here. What I actually have is 1 over 1 plus, you could write that cosine x squared as cosine x squared. That's what that means, right? Then times sine x dx. So this sine x dx is here. I'm off by -1, right? So negative du equals sine x dx. And I think I can rewrite the whole problem now. So this becomes integral 1 over 1 plus, this is u, so u squared, times negative du. Pull the negative out of the whole integral, negative du. The antiderivative of 1 over 1 plus u squared is arctangent, but I have a negative out there. So negative arctangent of u plus c, which is negative arctangent of u, but u was cosine x plus c. That's it. What do y'all think? No?
Slow down, you get the foolish man.
Show of hands. How many of you got the first one right? First one? Most of it? How many of you got the second one right? Not as
Get out of
many?
here with that.
Okay.
Hey, hello.
Any questions over homework? Do you have it right there with you? Which one?
I was just it's to the bottom.
15.
I was just confused. Oh yeah, I was gonna ask about that one.
There you go. If your notebook smells like skunk now, I apologize. I just can't get it off my hands.
That doesn't work.
Okay, so what is the variable that we are, what is the variable in the problem? X, because dx, that indicates the variable. Now, a and b we're going to assume to be constants. Right? Just any number, but it's fixed and we don't know what it is. So I heard something for you. What was it? 3ax plus bx cubed. Let's just see what the derivative of that would be. So what's the derivative of 3ax? Just 3a? Are we comfortable with that? Yes? Derivative of this? So the 3 comes down. The b is just going to come for the ride, so 3b x squared dx. That's what we've got, right? Since there are two terms separated by addition or subtraction here, I put parentheses around there. Now, do we have that up here? Kind of, right? Kind of. I'm off by 3. So if I divide both sides by 3 here, or if you'd like factor 3 out, then divide by 3, you're going to get a plus bx squared dx, which matches up exactly with all of this, right? So that whole part right there that I circled is actually going to be 1/3 du. And what's underneath the root, right, the radicand, is going to be my u. So how do you want me to write this? You want the 1/3 du? How about I do it this way? 1/3 du, right? And then since all this stuff has already been accounted for, I need this on the bottom, so square root on the bottom. So I just better put a 1 up there, right? And then just u, root u. And at this point, this is like one of the first things we learned with integration, which is the power rule. So we're just going to rewrite u as a power of u. Right? This is equivalent to 1 over integral u to the negative 1/2 du. And then just use your power rule. So I'm going to add 1 to this. When I add 1 to that, I get a half. So out front, I'm going to have the 1/3 that's coming along. I have 1 over a half, which flips and becomes 2. And I have u to the positive 1/2 and then plus some constant. 2/3 instead of 1/3 times 2, so 2/3. This is really the square root. So I'm going to go square root of u, but u was 3ax plus bx cubed plus c, and I'm done. Did that clarify everything for you? Okay. Was the trouble with the a and the b, like kind of like what are
I
those?
just didn't know what to make a u. I just didn't see it.
Okay. Okay. Which one? Can you read it to me? Sine hyperbolic squared x. That. Any thoughts on it? Sine hyperbolic. Sine hyperbolic x, right? For you? The derivative of that. What's that? You did? Oh, you did the whole thing? Yeah, the derivative of this will be cosine hyperbolic x dx. And then that's pretty straightforward for the substitution. Do you see it? Integral sine hyperbolic squared is going to become u squared. Cosine hyperbolic x dx is exactly du. That's 1/3 u cubed plus c. And then just replace u with sine hyperbolic. So how do you all feel about the substitution? The U substitution?
Easy, good.
Feel like when you left class you felt one way last time. Now you're coming back. Do you feel like you've gained some confidence in it with doing your homework? If you did your homework, you should have gained some confidence, hopefully. If you didn't do your homework, well, remember what all those other students were telling you? Good luck. Do another one? Which one? Uh-huh.
That'd be a sine pi t dt.
Sine of pi t dt, that's it?
Yeah.
Okay. So there's two ways to approach this. Last class I was telling you that if you're integrating a function with a linear expression in it, do you remember this?
Yeah.
That it's the antiderivative of that function evaluated at the linear expression plus c, but you have to scale by 1 over a.
So it'd just be
Remember?
1 over pi.
So you're going to have 1 over pi, because pi is like this is like ax.
Yeah.
Okay, that's exactly what it is. And then the antiderivative of sine, which is negative cosine. So make this negative 1 over pi, cosine of what though? Pi t plus c. That's the quick way to do it. And that's the way I prefer you kind of have
I just do the whole thing, so I'm too scared.
the way that you approach it. Now, if you didn't do it that way, then you would do this U substitution. U is pi t. And then you go du is pi dt. So you're going to replace this with u. Replace dt, well, you don't have much to work with. You just have this, so you multiply both sides by 1 over pi.
Yeah.
And then from here, you would get it. Got it? But if you have to do that on every single one of these later, it's going to take forever. Yeah. Any others? All right, so we'll move on. We are picking up 6.1. So this technique, integration by parts, is our next method, okay? So right now, here's what we have. We have power rule, right? We have, do we recognize it from Cal 1 as something, the derivative of something from Cal 1? So recognition, right? Those we'll kind of group together, okay? That's our basic techniques. We have U substitution, which is what last class and homework from last class was about, right? And what the quiz was about. Now we have a new method called integration by parts. And this is a formula that we use. Problem with it is that it's not a formula that works every single time with every integral. It's only when we have a certain thing happening within the integrand. All right, so I'm going to show you where the formula comes from first, then we're going to practice using the formula. All right? So I have up in the notes that if you were to sit here and call some function of x u, now usually we wrote this in like college algebra, we said y is f of x, right? Because y, we could graph it, but we could have called it anything, right? Let's call it u. And v is g of x. Then if we wanted to take the derivative of the product of these two, so if you say what's u times v, what's the derivative? You would use the product rule, wouldn't you? So you'd say derivative of the first one times the second one plus derivative of the second one times the first one. Yeah? That's the product rule from Cal 1. All right. Now this is where things get interesting. What I'm going to do now, and by the way, I'll mention to you, both of these are functions of x, right? So the derivative of u should be the derivative of this, which would be a function of x. And v by itself is a function of x. The derivative of v should be a function of x. And u by itself should be a function of x. So everything here is a function of x, isn't it? Okay. So what we'll do now is we're going to take that equation right there, because this is an equation, isn't it? This must equal this. What we're going to do is we're going to integrate it. We're going to integrate both sides of the equation. And I want you to pay attention to what happens here. What happens if you take something, right, and you take its derivative, and then you take its antiderivative? What do you think would happen? Right back where you started, right? You should just get u times v. So like differentiation, and then come through and undo differentiation, you should be back at u times v. So this is just u times v. Now this side, if I'm going to integrate it, I have to integrate the whole thing, right? But I have addition between the two. So I'm allowed to break this integral into two separate integrals. Like this, right? That's just using property of integration that if you have addition or subtraction, you can do them individually. Questions on that? All right, so the next thing I'm going to do is I'm going to take this right here and move this whole integral to the other side. So subtract the whole integral on both sides and leave this integral here, right? This is just like using equality. You can always subtract something from both sides or add something from both sides. So if I move this one over, subtract this integral over here, subtract it over here, you get u times v minus the integral of u prime v equals the integral of v prime u. Any questions on that? It's algebraic. No? Don't know what I did? Yes? Yeah? Just moving it around. That's it. Just moving it around. Right? If you have something that's positive on one side, you move it to the other side of the equation, it becomes negative. So that's all I did. All right, now what I'm going to do is I'm just going to kind of rewrite this, rearrange it a little bit. Anytime we have equality, right, we can always just write it the other way around. Right? If I say x is 4, I can also say 4 is x, right? So it doesn't matter. I'm just going to write this backwards now. So I'm going to write the integral, and watch this. I'm going to write u times v prime equals, and then this side over here, u times v minus integral v times u prime. So all I did here is I wrote this, but I switched it because it's multiplication. I'm allowed to do that, right? And then this side over here is the same, except here it was multiplication, so I wrote it that way. Okay? We're almost there. The only thing I did here was a slight change in notation. Instead of writing v prime, which meant the derivative of v, right? That meant the derivative of v. I'm going to write dv, which also means the derivative of v, right? And over here, instead of writing u prime, I'm writing du. So nothing has changed, just the way I'm writing it, notation-wise. Okay, this right here is the integration by parts formula. This is it. Yep, that's what we're going to call it in just a second. But let's get our heads around what's happening here, all right? What I'd like to do now, this is the one that we're going to memorize, all right? But let me just write it in different terms. This really means u was a function of x, wasn't it? So that was some function of x, f of x, times the derivative of v. Now remember what I had wrote up here. U was f of x, right? And v was what? G of x? Two completely separate functions, right? They're not the same functions. They're different functions. So f of x is u. Now dv would be what? G prime of x. And now what I'm going to do is I'm going to put dx because I can indicate the variable within here. Equals u times v. That's just these two multiplied, right? F of x times g of x. And then minus the integral of v, what's v? G of x. And what's du? The derivative of f. And then again, I'll write dx. See, that's kind of a longer formula to remember if you write it out that way. This is the shorter way of doing it. All right, so let's try and understand what the hell this formula tells us, all right? This is the most critical part of today, all right, is you understanding how this formula works. What we have is on the left side is the integral that someone gives you. You walk in, I give you a quiz, I give you this integral right here. And what you do is you look at that integral and you look inside of it, and inside of it when you're looking at it, you recognize two things. You recognize some function of x. I don't know, x squared, sine x, whatever it is, right? And next to it, you see some other function of x that has nothing to do with this function. But you recognize that it is the derivative of something. It's like maybe this is cosine, which you realize is the derivative of sine, right? Understand? Or maybe this is x squared, and you realize that's the derivative of 1/3 x cubed. Understand? And then, according to this formula, you can rewrite this integral as this new problem where this part has no integration in it at all, and you create a new integral. Do you see this as a brand new integral? What is the difference between this integral and this integral?
It flipped.
It flipped. What flipped?
The derivative.
The derivatives switched, didn't they? See, over in the first integral, this function that you identified, in the new integral, it's the derivative of that function. And this function, whatever it was in the new integral, is its antiderivative. Do you see? Yes? Okay. That's the heart of this formula. What it allows you to do is take something complicated, and hopefully this switching of the derivative makes the problem easier. That's what you're hoping for. But it doesn't always work. That's what I said. It has to look a certain way for this to be valuable to us. All right, so the integration by parts formula is what we call a transferring of the derivative. We are transferring the derivative from one function to the other. Now, this formula is the one that I said you need to memorize. And the reason is because there's a little cute saying that you can memorize to help you with the formula, which is right there. And you know what? I forgot to write it in my notes. I meant to write this in my notes, not the v prime. So look at this and then say to yourself, ultraviolet minus VOODOO, voodoo. So ultraviolet, U times V, minus, now there's an integral here, you just have to remember the integrals here, minus the new integral, which is voodoo. Voodoo. Right? Ultraviolet minus voodoo. I didn't make it up, okay? It's not my original thing. I learned the same thing when I was in your shoes. So, or you just memorize it, okay? However you want to memorize it. Now, you ready to see it in action? Okay, I think I have examples to work through. Yeah. So here are several examples. Each one of these on the side, I put a little note to the side of each of these that gives you a little more information about the type of problem we're doing. So let's look at the first one, part A, which is a basic integration by parts. This is about as simple as it's ever going to get when it comes to using the integration by parts formula. We have x times sine 10x dx. Now let's first appreciate the fact that there's nothing we can do walking in today with this integral. We cannot split this into two integrals, right? because it's multiplication? You can't just give me the antiderivative of this and this one separately? Basic U substitution. Do you see something in its derivative? 10x? What's the derivative of 10x? 10, but you have an x out here. Maybe there's a way it could work, but if you go and mess with it, it's not going to happen. So for u, for like a basic substitution, if you let u be sine x, the derivative of it is cosine x, right? Which doesn't appear anywhere up here. So do you all see that right now, a basic u substitution, no go? Yeah? Trying to see, make sure my microphone's working. Okay. No go with basic? So maybe we can use integration by parts. So what we need to do is we need to use the formula which says that is this on your formula sheet? Yeah, I think it is. Hold on, let me see. It's formula number 1. You see it? So what I'm going to do is I'm going to look up here within this function, or within this integral, and I'm going to see, is there something that I could call u, and is there something that I could call the derivative of some function, which I'll call dv. And what I want is that whatever I choose for u over here, its derivative is going to appear over here. And whatever I choose for dv over here, its antiderivative is going to appear over here. Understand? So you have kind of two choices here, don't you? Does everyone see clearly that there are two functions being multiplied? We have x, and you have sine of x, or sine of 10x, right? That's kind of our two choices. Now let's look at both possibilities here. If we let this be our u, then this would have to be the dv, right? And whatever you choose to be dv, you must bring the dx with it, okay? So that's one choice, right? That's one way I could do this. But let's analyze mentally what would happen in the new integral. In the new integral, we would have v, which means you would need the antiderivative of just this, right? Can you tell me the antiderivative of just this? You just asked about that, right? Sine pi t just a second ago? This is the same problem as that, except sine 10x, right? So you could do this, right? Negative 1/10 cosine 10x, right? That's what. So you're comfortable with putting the antiderivative of that here, aren't you? Okay? And then whatever we choose for the u, in this case would be the x, over here it would become what? 1. Ooh, that's nice, right? Because if it's a 1, then really the only thing that would be left there would be what? The antiderivative of that. So I would have a cosine function over here, but I would no longer have this x out in the front. Do you see that good thing? Now, what is another option? Switch it. So this is option 1, which I like. Option 2 would be I would do something like this. I would choose this to be the u, and this, along with the dx, to be the dv. Understand? Let's talk about what this would be in the new integral. In the new integral, I would need to have v, which would be the antiderivative of this, right? What's the antiderivative of that going to be? 1/2 x squared. So in this new integral, I think I'll actually write down this integral right here. This new integral would have the antiderivative of this in here, 1/2 x squared. And then times what? U would become what over here? Right? This u is going to become du. So the derivative of that, do we know the derivative of that? Yes, it's 10 cosine 10x, right? That's antiderivative. Right? And then I'd have dx out here. Is this integral nice? Why not? Why not?
There's too much stuff.
You still have two function multiplying.
Yes, but even worse, look, This one was x in front of a trig function, right? This one's now what? X squared in front of a trig function. It's actually become more complicated, hasn't it? Compare that to this one. I did it mentally, but I didn't write it down. This new integral over here, you said we would need v, right? Which is the antiderivative of that. We all said that that would be negative 1/10 cosine 10x, right? That's what we said. And du, which is the derivative of that, which you said was 1, right? So this would be it. Which integral would you rather work with? The first one, right? Because now this is just a trig by itself. No more x out front. See that? So by choosing the u the correct way, we were able to create a new integral that no longer has the x. So we actually kind of killed the x in the new integral, didn't we? And that's the key to integration by parts. You want to make a proper choice for your u and your dv so that in your new integral it's easier to solve. Got it? Now let's go through and work it formally now that we've thought about it. Still going to leave that formula up there. Here's where I do my work. Well, I'll get the formula out of here. It's right up. Well, I took it off the board. I'll put it over here. Integral u dv equals uv minus integral v du. All right, so this is the proper choice. Different people do this different ways. All right, so I always do my integration by parts the same way. I always start with a table. I make a table, and I'm going to fill the table in. The pieces of the table that will be given to me by the problem will be the two pieces of information that I had to identify, which were the v and the dv, right? Those were the ones in the original problem. So in this table, I'm going to put u here, dv here. The things that I'm going to have to figure out on my own is I'm going to have to figure out what v is and du. So the way I want you to think about this table is that this column is for my u stuff. This column is for my v stuff. I am going to plug u in directly from the integral. I'm going to plug dv in from the integral. When I go up in a table, I integrate. When I go down, I differentiate. So once I have u to get to du, I differentiate. When I have dv to get to v, I integrate, go up. Yes? All right, so what did we say our u was going to be? X. And we said our dv was going to be sine 10x dx. Make sure you bring the dx with you, okay? Don't forget the dx. I look at that and I get upset when I see no dx in here. So now, let's do the left side. Let's go down. So we're going to differentiate, right? For differentiate, I'm going to differentiate down. What is the derivative of x? 1, but I need to have the variable with me. So I'm just going to put 1 dx. If I divided both sides by dx, I'd have du dx is 1. And I'm just basically bringing the dx back over. Now up here, going this way, I'm going to integrate, right? So I'm actually integrating this, aren't I? To go back up, to get v. And you just told me what that was going to be. Negative 1/10 cosine 10x. Now no dx, because we integrated, right? We integrated, so we would put plus c here, wouldn't we? But I'm going to just, at the very end of my problem, I'm going to throw a plus c. I'm just going to remember plus c at the end all the time. You could bring it here, but it's going to complicate things. All right, you ready? That's it. We filled the table out. Everything from here on out is just plugging in. So this integral becomes, first of all, what? Ultraviolet, u times v, which if you look at your table is the multiplication of these two straight across, isn't it? So multiply x times this, and what would you have? Negative 1/10 x cosine 10x. Okay, good? Ultraviolet. See, no integral here, right? There's no integral in the formula, ultraviolet. Then minus, right? Minus, now an integral of what? v times du. V times du. So now we're looking at multiplying diagonally, here to here. So what's negative 1/10 cosine 10x times dx? Just that dx, right? So it's negative 1/10 cosine 10x dx. I'm running out of room here for my camera, so y'all with me? You see why it was so important to put dx here? Because if you didn't, then when you multiplied, you wouldn't have dx, and then the integral wouldn't be written properly. It would be bad math penmanship. And in the future, this is not going to be 1. It's going to be more complicated later. We good? Okay, so we're not done, right? Like, we haven't actually done that integration. What we've done is we've used the formula to convert an integral that we could not handle into an integral that we can handle. We have transferred the derivative to this, removed the derivative from this. So we have negative 1/10 x cosine 10x. That's this. Now, what do you want to do with this minus, negative, minus? Bring it out as what? Positive 1/10? And I'm still not going to integrate yet. I'm just going to leave this like this. We good? Have not done any integration yet. Just kind of cleaned up the inside. Now, let's find the antiderivative of this. So this is cosine of a linear function. What is the antiderivative of cosine of a linear function? It's going to be sine, right? So here's the 1/10 here times. So because this has an a in front, right, you have to scale by it. So 1/10 again. Antiderivative of cosine, you said, was sine 10x, right? Plus c. Does anybody have a question on where any of the numbers here came from? Yes? Good. Thank you.
The
Yeah.
second 1/10?
Okay. So just this 1/10 is from here, right?
Yeah, we pulled that out.
Yep. That was right there. So the antiderivative of cosine of this,
Sine.
antiderivative of cosine is sine. But remember last class we said that if this is linear, ax, you have to scale by 1 over a.
Yes.
That's it right there. See that? Yes.
What happens if, like, remember you did it the other way in red? If you got that, I guess, sort of problem, do you have to keep doing it like L'Hopital's rule, like over and over again, or how do you go?
Part C. You see part C? What we're going to do?
Okay.
Repeated integration by parts. But if you had done it the other way, the red way, you would actually have been going backwards. You would have been making the problem more complicated each step.
Oh, okay.
So it's not one of these things where it's like you pick U, you pick dV, like you make this choice, and you know what, if you get it wrong, it's okay, you'll eventually get there. It's not that. If you make the wrong choice, you could be on an endless journey. But you should hopefully recognize that the problem's getting harder and harder and harder. Each integral is harder and harder. So,
Still have you both after the
yeah. Okay, so the only thing I could do to clean this up a little bit would maybe make this 1/100th. And that's it right there. And then we could check it, right? I'm not going to. But you would have to do what? In this first term, you'd have to do a product rule. You get all that derivative taken care of. You come in with this derivative. You put them all together. You collect. You cancel stuff out. Whatever happens, this is what you're going to be left with. So do you see, we've undone, just by throwing a little x out in front of a trig function like this, it makes the antiderivative a lot more complicated, doesn't it? And that's what we promised, right? I promised this from the beginning. Undoing, right, reversing differentiation is a much more difficult process than differentiation is in Cal 1. Because in Cal 1, right, it's chain rule, product rule, and there's no variation, there's no deviation from those formulas. All right, let's look at the next one. A not so obvious integration by parts. This one's not so obvious. Arc sine pi x dx. So we run through a couple of things first. You know, is this a power? No, you can't use power rule. There's no x to a power. Is it something you recognize? Like, I hope everyone understands, like, you should recognize that you know the derivative of that, right? But not the antiderivative. That's not something you can recognize. Basic U substitution.
If it was just regular sine, then
We'd be done.
for sure. Right?
Yeah, negative 1 over pi
Okay.
cosine
Oh,
pi
that's
x.
right.
That's right. Yep. So does everyone see we're kind of, everything that we had before today is off the table? So integration by parts? Which means you have to come in here and you have to find some u. You are responsible for identifying a u. You are responsible for identifying the dv. The last problem, we chose our u to be x. We chose our dv to be that cosine thing, right? Or was it sine? I don't, whatever. We need two things, right? But if you look at this, this is really just one thing, right? This is not multiplication in here. This is arc sine of pi x, right? This is the argument of that inverse trig function. So this is all one clump of shit. You can't pull this apart, right? This is all one big piece. Which means that the only other thing left is that piece, right? So you only have two choices, right? I mean, there are two things there, I guess is what I'm trying to get at. This right here and the whole thing.
So you can use the function within a function as an argument? Are you kidding? Because in pi over x, or pi x, isn't that a function within?
Okay, you cannot choose as your u a function that is inside of another function. It has to be separated by multiplication. So the formula is this, right? U times dv, not u inside of v. Now, if that were inside, if we wanted to do it, that's basic substitution. That's what U substitution is, right? You're looking for something that's inside, the derivative is sitting on the outside somewhere. Any ideas?
dv is dx.
dv is dx. Now, let's think about what would happen here. If dv is dx, you would have to integrate to go back up, wouldn't you? And this is like 1, isn't it? So v would be the antiderivative of 1, which would be x. So that would be there, right? So that's doable, isn't it? That's doable. But that forces you to use the other part as u, which would be everything, arc sine pi x. With me? And now you have to differentiate to go down to du. Can you differentiate the arc sine of pi x? Yes. Right? 1 over square root of 1 minus x squared, but in our case, pi x squared. So I'll put pi x squared. Am I done with the derivative?
No. Yeah, it's just pi.
Times the derivative of what's inside, so chain rule, so times pi. And what do I need to slap on the very end of that? Nope, that's integration. dx. I know that's kind of hard to read. I wrote that kind of small, but you'll have that? Any questions? Whew. Okay. Now, just for the sake of showing you, I want to see what other option there was. You have to choose v and u and dv. So another way you could have done it is you could have put dx here, and you could have put arc sine of pi x dx here. Do you see that? Major problems here. First, you have to integrate up. To integrate this up, guess what? That's the original problem. which you can't do to begin with, right? So there's no way you're integrating this thing up. The other thing is, what's the derivative of the derivative? That's going to be like a second derivative, which we never want that happening. So you never want to choose u to be dx, ever. Understand? Another way you can look at it is, if you choose that to be 1 dx, what's the derivative of 1? It would be 0, right? And then it's going to, look, this is so ridiculous. Watch. I don't think I've ever shown students to this before, but if this is 1, the derivative of 1 is what? 0, and then v right here. Well, I don't know what it is. I have to wave my hands at it. Isn't it this integral? And I'm telling you, like, I have no freaking idea how to do that, right? Like, I need to integrate this, but I don't know what that is. Yeah? Okay, do the formula. This original integral would be what? U times v. What's u times, u times v. It'd be this times this, right? Minus v du. What's v times du? 0. So guess what you have? That this original integral is? This original integral. Congratulations. Thank you. Blue is equal to blue. I'm happy for you. I mean, you haven't gained anything on that. You see that? You've just kind of confirmed that the original integral you were looking at is the integral you're going to go and try and find. You've gone in a circle. Useless to do it this way. Understand? Okay.
Is it a good way of, if you're working and you're a little unsure, which one should I set up for my table? Is that a nice quick check? Oh, look, it'll figure out. It's going to put me right where I started. Obviously,
You could, well, if you ever are trying to put du to be dx, you know right away you're going to get back to the original integral.
Right.
Okay? The thing that should tip you off is when you choose dv, you better be able to integrate it. If you can't integrate dv, you're in trouble, right? All right, so let's move on here. We're not done. This should turn into ultraviolet, which is going to be this times this. So that's just, I'll put the x in front, x arc sine of pi x. Do we agree? Minus integral voodoo. Ultraviolet, this times this, minus integral of voodoo. This times this. Oh my goodness. This times this, right? Oof. I think I'm running low on room here. I think I'm going to move this. I'm going to move the whole thing over. The original integral is equal to ultraviolet minus integral of voodoo. V times du, which was 1 over the square root of 1 minus pi x, that quantity squared, times pi dx. Everyone see voodoo there? Voodoo, voodoo. And then you look at that and you're like, whew, why did I take this class? Because I have to. And why did they make you take this class? Because they want to see who can and can't do it. That's right. Trying to weed you out. Sad story is that's the truth, especially for you biology majors. Engineers need to do well in Cal 2. Biology majors usually don't have a vested interest in mathematics the way an engineer would. So this is almost like punishment. It's to thin the herd of doctors, that people who want to be doctors. Engineers just need to, I guess, get to a point where you're thinking this way and you enjoy thinking this way and you like this stuff.
like the way it reads.
Yeah, when it all kind of comes together and All right, so now we look at this and you start asking yourself, did you gain any ground?
Yes.
you know, you look at this new integral, look at the original one looked nicer to me than this, right? It was just, what was it? Arc sine pi x? I don't know, maybe not. But there's no more arc sines in here, right? There's no more inverse trig functions. You look at that and you're like, crap. So does anyone see it? Just a basic u sub. This is a basic u sub. Let me do something here. Let me actually square this. So what happens if you square pi x? Pi squared x squared, right? That's what you get. What is the basic u sub that you see? Pi squared x squared is your u. Why would you use that? The derivative of it would be linear, wouldn't it, in x? Because this is x squared, so the derivative of it would be linear. And that's linear, isn't it? But I argue you could go even more.
Minus
1 minus this would be even more, and the derivative of it is the same, isn't it? So do you remember how last class I said you have to be kind of masters of this by the next class? This is why. This is a somewhat basic u substitution problem, but if u substitution is something that you're going to get to next week, then it's very difficult to follow along in here. So at this point, what I'm going to do is make a u substitution. So this is like my new universe is this problem. Okay? This is my new universe right now. I'm just going to work that problem out. So remind me that we need to come back to this and tack this onto the front of the answer. So working with that integral right here, I make a u substitution. U is equal to 1 minus pi squared x squared. The derivative of this will be, you tell me, negative 2 pi, what? Look, pi squared is a constant, isn't it? Negative pi squared is a constant. It's just going to come along for the ride, isn't it? Negative pi squared. Derivative of x squared is 2x. So negative 2 pi squared x dx. Now you look back over at this integral right here, and you say, do I have that, or can I match anything up? Well, do you see what you do have over here? Is a pi x dx. So let me just rewrite this over here. Du, see, negative 2 pi times pi x dx. What I did here is I just kind of peeled off one of the pi's so that I could see pi x dx here to match it up with this. See me matching that? So what should I scale by on that over there to make these things match up? Negative 1 over 2 pi du is equal to pi x dx. And that allows me to rewrite the whole problem. What's in red is going to become what?
Du.
Almost like all that du, right? Like negative 1 over 2 pi du. That's what this is going to become. And then I'll have like a 1 over the square root of u. So just this green thing is going to become 1 over the square root of u times negative 1 over 2 pi du. Take the negative 1 over 2 pi, take it out. Change that to u to the negative 1/2, right? And then integrate. Got a question?
Will that become positive?
I'm not even, look, remember I said my universe is here?
Oh.
Okay, I'm serious, my universe is like right here. I'm only living from like here to here. Because my signs are going to get messed up if I try and incorporate all this stuff. So I am not even caring about that negative right now, okay? I will come back and get that. With me? Now, as you move on and get better at this, you can do it all at one time. All right? But I would go slower steps initially. Okay, so what's in this green box becomes negative 1 over 2 pi integral u to the negative 1/2 du. The antiderivative of u to the negative 1/2 is 2u to the positive 1/2. So I'll have negative 1 over 2 pi times 2u to the positive 1/2 plus a constant, right? But I'll throw that in at the very end. Just going to remember. 2's cancel. Negative 1 over pi square root of, what was u? 1 minus all that junk, right? 1 minus pi squared x squared. Plus c. I'm going to bring it at the end. Because this isn't my final answer, right? This is just that green part. Yeah, now I need the ultraviolet minus this, right? So everything, well, I erased the formula, oh well. Everything I had done up to that part was just integral v du. That's what I just finished up. So I need to bring ultraviolet minus in now, in front of that. So you ready for the final answer? The original integral, which was arc sine of pi x dx, is equal to ultraviolet, which was, I don't remember, x times arc sine pi x. Okay, so now I'll do it in a second. Minus now this, right? So another negative 1 over pi square root 1 minus pi squared x squared plus c. And the minus become plus right there. So equals x arc sine pi x plus 1 over pi square root 1 minus pi squared x squared plus c. Of course that's the antiderivative of arc sine pi x. It's obvious. We're done. What do y'all think? You're going to need to practice. I wonder how quickly we could show that this is the derivative. I want to. I want to prove to you it is. I'm going to go fast, though. Product rule here. Derivative first is 1 times the second. Plus derivative of this one, which is 1 over the square root of 1 minus pi squared x squared. That squared, right? Times derivative of what's inside pi times what's out front x. Plus 1 over pi. Now, derivative of the square root of something is 1 over 2 roots of that something. Times derivative of what's inside, which is negative 2 pi x. Derivative square root of something is 1 over itself. 1 over 2 times the root, right? Times derivative of what's inside. Derivative of what's in here is this.
I thought you just made the square like I thought pi squared was just a constant.
Where? Oh, I'm missing the square. Thank you. Yes. Good. Yes. Okay. Y'all see it? Look. 2's cancel. 1 of the pi's cancel. So all this is negative pi x over the square root of that junk, right? That's what this is. Because see the negative here? That's negative this. Plus over here, what is this one? Pi x over the junk. Square root of junk, right? Positive, take away the same thing. They're gone. What's left? This. So it checks. And it better, yes.
I remember you said that 6 people dropped your class. Was it around this time?
Yeah, right?
I don't know. Maybe it was after the first test. Yeah, I don't know. Look, every one of you can do this, all right? It's a matter of how much are you going to put into it? How much commitment are you going to make to this? I mean, this is not natural thinking here. I mean, it's not natural thinking. It's just, it takes a while to get used